Okay, so welcome back to another video. So here we have this pretty long limit, but the result actually does come out nice. And that is that we have the limit as n approaches infinity of n to the power -1/2 multiplied by n plus 1 divided by n. That's just the exponent. And then multiply this out by 1 to the power 1 times 2 to the power 2 times 3 to the power 3, all the way up to n to the power n of the quantity and then the exponent of 1 divided by n squared. So as mentioned, it's a pretty long limit, but the result does come out nice. So I think it's worth noting that you can see that from this expression over here, we see that this has to be in the form of a partial product series. And then I guess you can fill in the gaps of like, what is that series that is being, expanded upon. But if we actually just apply a bunch of, algebraic and also the calculus as well, and then once we get to that certain point, then everything will just make things a little bit easier. And especially utilizing, the natural logarithm too, as we see with exponents and then, all the base itself. So I think that'd be pretty important to actually utilize that. So let's actually just jump right in. So worth noting that this expression is the product expansion 1 to the power 1 times 2 to the power 2 times 3 to the power 3, all the way up to n to the power n. We see that this partial product series is written from k is equal to 1 of n of k to the power k. And so if we call this entire limit L, then so far we could just substitute this back in and say that limit as n approaches infinity of n to the -1/2, then n plus 1 divided by n, that's the exponent. Then this entire thing is just filling with the partial product series, k to the power k, and then its exponents of 1 divided by n squared. Now let's actually take the natural log of both sides. So we have the natural log of capital L is equal to so the limit, this is with continuity, of course. So the natural log of this entire expression, so let me write this out in full first. And so from here, let's actually apply all the natural log rules into this expression over here. Obviously, we see that we have some exponents and we have some products of these, bases. So let's actually use those rules and see that easily we can see that this is, so we have the limit as n approaches infinity. Then let's see, the exponent can come out to the front, and then we have the natural log of n, so this can be written as n plus 1 times ln of n. Then we can just divide this by 2n. Now, same thing over here, so 1 over n squared can be moved outside after the utilizing the natural log properties. So 1 divided by n squared, and then the partial product series n, and then k equals 1 of k to the power k. Hold on, I forgot one more thing. I forgot to put the natural log in here, so let me say it first. And now by applying the continuity of natural logs, we can actually use the notation that the natural log of a product series is actually equal to the sum of the natural logs. So what we're going to do from here is we're actually going to evaluate this expression first before we can continue on completing the rest of the process. So starting this off, let me actually move to a different marker for this one. So starting with the natural log of this product expansion, so ln of this partial product series over here, then obviously we can see that we write this as the partial sum from k is equal to 1 to n of the natural log of k to the power k. Then we can move that exponent outside, so this will be the natural log, the sum, the partial sum, and then of k times ln of k. And so from here, we're actually going to utilize a little trick, and that is we're going to add and subtract this following term. So add / subtract. We will be using this term. We will be using the partial sum, k is equal to 1 of k times ln of n. So by doing so, we have, I'm going to write this out in the same again. So k is equal to 1 and then k ln of k. This is simply equal. So I'll put that same thing as before. And then afterwards, I'm going to add and subtract the terms that we're going to be using. So ln of k, then we put this as k times ln of n, and then add this with the partial sum yet again of the same series, ln of n. And now from here, we're actually going to use these, again, by continuity of these, sums and the natural logs, then I can actually apply the natural log properties, and I can, since it's under subtraction, then the input is under the division. So here, this is k equals 1. So we have k then times the natural log of k divided by n, then subtract or plus the natural log or of that partial sum. So k ln of n. This part over here is actually a little interesting here because the sum is depending on k and not n. So the natural log of n is a constant in this situation. So we actually see that we can actually factor out the ln of n outside of our sum, and notice that, so let me write this first. So we have ln of n, then multiplied by this partial sum, k is equal to 1 and then of k. K is actually, the closest form is given for the sum of the n of the k natural number, or rather, no, that's right, n natural numbers. And so that gives us this form that we can write this as n times n plus 1, and then just multiply the ln of n over here, then this is just divided by 2. So from here, we can actually make this substitution over here, and then continue on with the calculations, so on. So denoting this equals from coming from this calculation over here, then I can say that now we just plug in between the lines and the gaps and say that we have so far the partial sum k times ln of k divided by n, then add this with n times n plus 1 times ln of n, then divided by 2. With all this, now this is clearly to see that this is as further as we can go, then this is actually now put that back as the ln of the natural log from k is equal to 1 to n of k to the power k. Now let me fix this arrow over here. So now after all this, so we can now just plug this back into our like everything that we just simplified for specifically for the product series. And so I'm actually going to draw this line over here to further imply that we can continue on with the calculations. And now we have that this is negative then n plus 1 times ln of n divided by 2n. Add this with 1 divided by n squared, and so we just distribute all this into here. So this is, and I'm actually going to do a little bit of a trick here as well. So when I'm going to distribute the 1 over n squared into this sum, I'm actually just going to take that part of the 1 over n and put that inside of our sum. So this will be 1 over n and then multiply by this partial sum, and then we have 1 over n multiply, or actually because there's a k, so k then times ln of k divided by n. All right, and now just distribute the 1 over n squared to this part here, but you'll notice that one of the n's will cancel, so this will be this will get rid of itself, and so this is plus n plus 1, then multiplied by ln of n, and then divided by 2n after just multiplying that n into the 2 from the denominator over here. And so easily enough, we see that terms cancel each other out, specifically this part here and then this part here. So now all that's left is we just got to calculate this partial sum over here. So all that's left, 1 over n, then the partial sum from k is equal to 1 to n of k divided by n, multiplied by ln of k divided by n. And so to further establish and see that so far we have made the justification to say that the natural log of capital L is equal to this limit over here. So let me first write that out full. So after all this, now you might be thinking, where can we go from here? How can we actually exactly evaluate this partial sum? If you actually pay attention closely, and then with this limit, this actually satisfies a very well-known definition, specifically the Riemann sum or the Riemann integral. So in other words, after plugging in all the pieces, you find the right ones, we can actually see that this is actually going to equal the definite integral from 0 to 1 of x times ln of x dx. And so this is actually a very easy calculation to do, since what we can do is we can actually apply integration by parts. So if I let u equals ln of x, then dx, or excuse me, du is going to equal 1 over x dx, and then choose our dv. In this case, dv is going to equal x dx, then v is going to equal 1/2 x squared. Now just plugging all this together, so now the following we would have now is that so far ln of L, capital L, is going to equal x squared, then ln of x, all this being divided by 2, Then we just evaluate this from 0 to 1. Then we subtract with this integral from 0 to 1 of v times du. So one of the x will cancel. So then we have an x divided by 2, then dx. All right. And then I'm just gonna skip the calculations, and you see that if I plug 1 for all this, that's gonna equal 0. But if I plug 0, be careful, we have an ln of a 0 that's undefined, but you can actually just apply using L'Hopital's rule to get to the point where this entire term itself is actually going to equal 0. And so all that's left is calculating this integral over here. And so if we just take the definite integral of x over 2, that's obviously gonna be 1 over 4x squared. Plug in 1 over 4, 0, 0. So therefore, this is actually ln of L is going to equal 1 over 4. Well, it's a minus because we have a minus over here. And so just take the e base to both sides, and we have our final answer that L is going to equal e to the power negative 1 over 4, which is exactly what we wanted to calculate this entire time. And just like that, we are done with our computation process. We have figured out what the result this is going to equal to. Very nice indeed. And so yeah, that's pretty cool if you ask me.